Welcome everyone for Chapter 5 under the Payment Management System class, and in this chapter we will be talking more and more about the Payment Management System databases and how can we manage it in a way to be efficient and to get us to the ultimate solutions and ultimate benefits out of the Payment Management System. So from the very beginning, database systems, what are the elements of the PMS systems and how can we manage it? So the database system is simply a computerized record keeping system nowadays. Back in the days it used to be more of a paperwork that you need to fill and keep it in your desk. Now everything is in a computer system where you would keep all the information once you get it from the field into one single system. So the system, it has an overall purpose, and that purpose is really to maintain the information as well as making that information available on demand, or when we want to do a study, or if we want to decide on how can we fix certain payment section, then we have to go back to the database and decide on the technique that we need to use to fix that problem. So while we're talking about databases and how can we manage database, we need to think of several questions that we need to ask ourselves as well as anyone who's going to be dealing with such database. The very first question would be what data that has to go in. That's very important. There's so many data that we can collect, and I mentioned this in the previous chapters. We can have too much of data, and when it comes to storing this data, we have to ask ourselves where and what data has to be selected out of the clouds of data to be included in the database. The other important question would be who puts it there. Is it going to be you, the payment engineer, or a technician, or one from the managerial level? Because this is also going to be an important question that we need to answer. The third question would be when it goes in, and the question here really related to the frequency of how much data that we measure and when do we need to put it in the system. For example, in some state DOTs, they would measure the payment performance every other year. So every other year they would go to the field, measure data, but now we need to transition those measured data from papers to the database, and we need to set a due date that all the information has to be transferred to the computerized PMS database. Otherwise, if it stayed in a paper, it's going to be really impractical to use this data in the future to decide what to do to fix any payment section. The following question would be what analyses are performed. What type of analysis are we talking about? Is it just going to be a cost analysis? Or is it a prediction of the amount of fatigue cracking? Is it a prediction of rutting? So that also need to be included while we're trying to manage the payment management system database. The following question would be when and what changes are made. Do we need to change the criteria of measuring certain crack, the criteria of differentiating between low, medium, and high severity, or the criteria of the sampling units? How many sample units do I have to get from each one of those sections, and so on and so forth. And eventually the last question would be how it comes out. Now we feed the system all the information, all what we need to do, we do the analysis, and now how are we going to present such data? And that would be the last question to ask ourselves while we're trying to manage such database. Now one of the old folks may ask, so what's the big advantage of a database? Why don't we just keep all the information in paperwork forms? We keep stacking them, and whenever we need something we'll get back to those paperwork. It becomes very hard by time. Now we're dealing with a lot of sections and intersections and different mixtures and different conditions. So having a computerized database really gives us the advantage of storing the data in a very compact space rather than stacking lots and lots of paperwork on top of each other, as well as it gives us the advantage of storing as well as retrieving accurate, up-to-date information in a very fast mode. The other advantages that we can have based on computerized system is centralized control over all the information. Sometimes again, if we are dealing with several divisions that they keep collecting data that it's related in a way or another to the payment management system, it's hard to keep track of those. While if you just have one computerized system, you can have a central control over all the information that was gathered from different divisions and different physical places. So speaking of those advantages, we need to keep in mind that this is really going to require the system to be well designed and well maintained with the concept of centralized control in mind. Otherwise, it's going to be difficult to keep track of every single details in the database. Another advantage of having a centralized database is really now we are going to reduce the redundancy by having each piece of the data stored in only one place. And we see this often and often when we go to a paperwork system where we see lots of information just simply are repeated here and there because we are not sure if, let's say, how many lanes per direction was collected before or not. So we would keep measuring and collecting and spending time and effort collecting data that was already measured previously. While if I have a centralized database, it would tell me right away if this data is already collected, then I need to concentrate on some other data. The other advantage also, the data can be shared by various applications, so that's a big advantage as well. Another advantage of having a centralized database is now I really can enforce some standard ways. For example, if I can have a reinforcement on the way I name the data, the way I format the data, and even the way I document it. So if I do not have a centralized database, everyone or every personnel, or sometimes I have a technician that he or she has been collecting the data and naming the file certain name, and all of a sudden he or she retired, and now we have a new guy doing this, and all of a sudden now there is no standards and there is a new way of doing it. And from a research perspective, now we're trying to go back and look at the data, and all of a sudden we see discontinuity in the way we name data or the way it was formatted, and all of a sudden we go through a struggle time because there was no standard way of naming and formatting and documenting the data. So a big advantage of having centralized database is I can define what are the standards that has to be used, and I need to enforce them from the very beginning, and everyone will follow them from now on. The other advantage would be the data security. It can be really enforced to control updates and flow information rather than just having it all over the place and everyone can, some unauthorized employees can have an access to it, while if I have a centralized computerized system, I will make sure that the data is secure. Another advantage here also of having a centralized database is any conflicting requirements can really be balanced to optimize the database, as well as a big thing also is integrity. The integrity can be really maintained, which is eventually we're trying to avoid having incorrect information. So once I have that centralized feeling of a database, integrity would be kept. The other side of the accuracy of the data besides the integrity is the spatial identification requires being able to physically relate the data to the location of the payment network. So many times we know the information, but we have a hard time to relate this type of information to the payment section in the network itself. So having again a centralized database would help us to identify and correlate the data to the location into a certain payment network. While the temporal identification is different. So spatial was, we already mentioned it, now temporal identification really defines when the data was collected and placed in the database. So it's really like a stamp. Time and data stamp are very critical for performance monitoring of payments. Sometimes again we need to go back and see when did we collect the data. Sometimes when I collect, let's say, fatigue cracking again, and for example, if I plot fatigue cracking versus time, this is here fatigue cracking versus time, and now fatigue cracking was going up with time, and then all of a sudden it goes down, and then it goes up again. And you may wonder, what's the problem in this point here? So the problem, sometimes we go, if we have a very good centralized system, then sometimes if there is a change in personnel or change in standard, we would be able to know what happened here exactly, rather than if it's a true drop, that means there should be some maintenance happen. But sometimes we go to the database and we cannot find any maintenance activity that triggered this drop in fatigue cracking, and the only reason would be changing personnel or changing standards. So having a centralized system will give us the chance to know the time and the data stamp for every single data point that was selected, and that is a huge advantage from the perspective of accuracy and performance of payment in general. So what are the components of an ideal database? So to have a good successful database, you have to have the good hardware, which is simply a computerized system. You have to have an accurate data. You have to have the right software to manage all the information and store it and do the analysis and predict and recommend the right selection of maintenance techniques, all the way to the right people, the right personnel that they are going to be working on the system. So it's a combination of all those four components together. This is here a schematic of all the pieces that we need to have in the database system. First of all, we need to have the users, which are the personnel, which are going to feed the data into software. So the software all the way to the data, and the data has to go to the hardware as well as the software. So as you could see, the major thing is really to have the data, which is gonna need hardware to be stored in, using a software to analyze, and all this need to be managed by good trained payment engineers. So let's talk about first of all the hardware. Hardware, typically, as you may expect, it includes all the physical devices which is gonna be eventually used to enter, store, manipulate, all the way to retrieving the data. In fact, the figure 2 that I'm gonna show in a second shows the basic hardware used in payment management system database. So this is here the figure that I'm referring to. As you could see, the storage devices, this is kind of an old picture, but going from floppy disk, hard disk, now we're using hard drives, external hard drive, we have flash drives, but eventually all these information are gonna feed into the central processing unit. The central processing unit now is gonna be connected to processing or input device like a keyboard or a mouse or so on and so forth, until we do the analysis, and eventually we need to have an output where it's going to be connected to either a screen to see the information, or we print out the report, or we have a plotter to plot the entire city or the entire network to see the overall health of the payment network. Also under the hardware part, the most important hardware consideration is really speed, which is measured in turnaround time. That's very important. Back in the days it used to be an issue. Now it's improving more and more, but we need to keep in mind running a big database would require a high-speed computers to run the simulations, predict the performance, and recommend what do we need to fix those roads. If the time taken to do this is long, this is gonna demotivate engineers as well as technicians to use the entire payment management system, and we're gonna lose the interest of using it. So it's very important to consider that, especially the time which is between making the request and seeing the results. So, and here I'm giving you one of the rule of thumbs is smaller than 5 minutes. This is the typical time back in the days. In fact, now the processing time has gone lower and lower, but we need to keep that in mind to reduce. How can we reduce the amount of processing time as much as we can? Moving now from the hardware to the data. The data is very important, and without measuring the data, nothing can be done. So we need to identify what type of data that we have. Is it just inventory data? Is it performance data? Is it climate data? Is it information about the structure of the pavement sections? How about the amount of the data? This is very important. Do we need to collect 70% of the section area? Do we need to collect 50%, 30%? The amount of data is very important, as well as the characteristics of the data. The rule of thumb again that the types and the amount of data have already been discussed, as I mentioned you before, but again I just wanted to put it here one more time to let you be reminded that you need to know what's the amount of data that you need to have and what's your needs in terms of project level versus network level. So under the data, there is several characteristics of the data that has to be maintained, and the very first one is the integrity of the data. So the way I can explain integrity here is this little example, that if we have two different pieces of data profess to present the same fact, they should be equal. They must be equal. Otherwise, again, the data is not well maintained, and the integrity of the data is really compromised. The other aspect besides integrity is accuracy. Accuracy, for example, the values has to represent as close as possible to the actual situation as indicated in the location as well as the time. It's the most often a data collection consideration. If you have an accurate data, people are gonna trust it, are gonna use it for their analysis, and they would feel comfortable coming up with recommendations and conclusion based on accurate data. If the data are not accurate, everyone would question it, and everyone would question even the recommendation that's coming out from such data. The third characteristic of the data is validity. So the given value or the given data, is it correct or not? Validity is typically tested by comparing the given value with a range of reasonable values from the circumstances. For example, if I go to certain place, and that place typically the average temperature at daytime and summertime is 70 degrees, and I went and I sent the technician to measure the air temperature, and he found it's 90. So the data here is not valid. It's very far away from the reasonable range of temperature at that time of the year. Same thing for performance data like fatigue cracking. Typically, if I have certain performance, let's say the rutting is typically at this area somewhere between 0.1 to 0.2 inches, and all of a sudden you have a technician that giving you a value of 0.75 inches, then this point or this data is not really valid anymore, and you need to question it. The other aspect also under the data consideration is security. If the data, for example, are destroyed, you must make sure that they should be restored, or they can be restored. So read-only option is very common, and using a password is another common practice. So sometimes you, as a payment engineer, you will be the only one to have the ability to read and modify the information, while when it comes to other technicians or other people that they are accessing such system, they would just be able to read it but not able to modify the system. Same thing with using a password. Everything has to have a password to access the information, to prevent anyone else to get into the data and alter the data. So when it comes to backing up the data, it depends on the importance of every piece of information you have in the system. So, and here we're going to go through different levels of accuracy and importance of the data. So you've got some basic scratchpad data, and those are not really important, and you can have little concern for losing them. So backup as changes occur, and some of the examples to have as scratchpad information would be just definitions and some policies. So this is the example. If you are just defining some of the information or a policy that you use, it's not that important, because you know there is several copies on the internet or some other places which will give you the assurance that even if you lose it, you are gonna have another copy. So for those type of information, you can just back them as any significant changes happens. Other than that, you're not gonna really do a major backup data for scratchpad data. Moving now to important data. Important data are really important but not critical. So the way to deal with the backing up the data here is 2 backup copies, 2 days per week. You see, it's very important to back up the data and spend that much time every week to do that. So it's 2 days, 2 times per week you need to back up your data and archive copy every 1 week. So every 1 week is archive copy, and regular backup twice a week. Example for important data is simply training documentation, any calibration information, and certain procedures that you may develop from the project level perspective. Going now to the critical data, which is the most important one, are critical to the entire operation. For example, inventory data, performance data, traffic data. All those pieces of information are very important, and you need to have a daily backup and a weekly archive. So you see here, from scratchpad data to important data all the way to the critical. The critical really are, as it says, it's critical because now you would send a technician and they would spend a day or two for a certain section to measure inventory data, like the geometry of the section, how many lanes, and traffic information, which again takes a lot of time, all the way to performance information, this is the most time that we spend in the field collecting fatigue cracking, rutting, thermal cracking, and so on and so forth. And definitely you don't want to lose those information, and that's why it triggers more frequent backup, like a daily backup and a weekly archiving. Another thing that we also have to keep in mind, and it's very critical and very important, is to have a data dictionary. In so many databases, especially naming certain columns or certain rows or even certain file name, it becomes very hard to track the name meanings, or what does A, B, C or certain numbering really mean. So the dictionary is very important. Some of you may go to the LTPP database and see in one of the columns it says FC, and that will be fatigue cracking, or ALG, alligator cracking. You won't see the entire words mentioned. So having a dictionary would really define the data elements used in the system, and also it's going to describe the meaning. It's going to tell you what's the unit of measurements, what was the format, where was the source, and how can we use the information, and if there is any relationships between one column of data to the other one. So it's very important, when typically we would again store it, and we need to keep it and update it by the time we introduce new data to the system. This is here a very old style of a data dictionary, but I'm pretty sure if you go to the LTPP database, you would find one single file that explains every single name of a column or a file, and what does it really mean, and what's the unit that was used for. But this is here just an old example to show you how did we used to have it. So you see here we've got codes, code 1 to 18, and every code has a meaning. So by the time you see number 1 in any page, this means it's a rural interstate, or if you see a number 12, that means it's an urban freeway or expressway, and so on and so forth. Now moving towards the third element in the database system is personnel, people, you basically. So you would be the payment management system engineer, probably the only one who took this class, and you would be able to administrate typical responsibilities such as defining what data are to be stored in the database and what data should not be stored, the extent of the data, the amount of the data. It will be your sole responsibility to fix and maintain the database. So as an engineer, payment management system engineer, you also have the capability to decide the level of security for each piece of data, and also you need to define for others what's the backup procedure. Is it every day? Is it every week? How about archiving? Same thing. You also have to define the integrity and validity checks. How can you double check that the data is accurate, that the data are valid? You need to come up with a procedure to make sure that the system is validated, the data that you are using is accurate, so you can build accurate predictions and conclusions. On top of that, as a payment management engineer, you also have to decide the level of accuracy. You need to maintain the data dictionary. Sometimes, as I said, you may include extra amount of data, and therefore you need to define what does each new column means, and what's the unit that you used, and what's the standard that you implemented. Also, you need to decide the storage structure and the access strategies. Are you going to be the only one who are going to be accessing the information, or if there is other technicians or other engineers that they will access the system? How much access privileges do they have? All this you need to define. You need also to monitor the performance. This is very important. What's the performance of the database? Is it acting right? Is everything going to the right direction? You also have to be responsible for coordinating and communicating with other users. You also have to be responsible for to changes, any changes like changing requirements in the database, as well as defining a strategy for backing up and recover the data in case the data is lost. This is here a simple schematic for the database triangle. So the system administrator, mainly it's going to be you as a payment management engineer, and then you would have two sides. One side is the data processing expert, as well as the technical subject expert. So from the technical subject expert, the database engineer's aspects are going to be involved mainly on integrity, accuracy, validity, and security, while the data processing experts are going to be looking for more of an operational aspects of the database. The question now that comes into place is, in large systems, a group of people handles the administration. So in PMS system, the PMS engineer would be the administrator in this case. So as I mentioned in the big triangle in the previous slide, you as a payment management engineer would be the administrator that under you there will be other engineers to handle the accuracy, validity of the data, as well as other experts of the operational aspects of the system. But again, typically in any DOT you would have one or maximum of two payment management engineers to have an overall view of the entire system. So it's a big responsibility. So underneath you as a payment management engineer, you would deal with an application programmers. Those are the ones who are going to be writing and maintaining applications, programs in order to access and use the database, and they must have a good data processing experience. So it's not just about programming, they also have to be engineers in a way that they would deal with the data in an engineering sense, and they can process the data in the most accurate way. So application programmers have the following functions, and you should give them those privileges. They should have the capability to add data. They should have the capability to retrieve data. They also can delete some of the data, manipulate the data, all the way to creating new data. So all of those has to be acceptable privileges that need to be given from you as a payment management engineer to the application programmers. From the other end, there will be also end users that they will be using your database, viewing data, and those end users can be casual users. Those casual users must be allowed to only access the database through the application programs, which will produce standard reports. They cannot really change the data. Standard reports are the same regardless of who and where they are initiated. So some of the examples here is detailed condition data report, cost report, history report, performance predictions. Those are this type of standard reports that casual users would just go to the database, print, and get those outputs out of the system. While other type of end users would be frequent users. Frequent users should be allowed to retrieve the data using the database system functions, like in a figure that I'm going to show in a second, and also they should have some experience with databases. It's not just casual users to go and print some reports. They should have now more experience related to data. This is here a schematic for software usage all the way to the users. So the system administrator should cover the entire process from the beginning all the way to the end. So here you would see the application programmer. Those are the ones that they have lots of responsibilities of adding, retrieving, working on the data, and then they would be dealing with the software, and that software is going to include operating system, database management system, all the way to application program. So for casual end users, they would just use the software from the application program perspective, meaning again they will just be printing and obtaining some basic reports. While frequent end users, they will have the same privileges as the basic casual users, but also they would have a big and significant access to the database management system, and that's why we said they should have to have a minimum amount of experience in dealing with the database itself. So once again, the entire system here is gonna feed back and forth to the data, which is gonna need definitely a hardware. And the question that you're gonna ask yourself, where am I as a payment management engineer? Again, you are the administrator. You are gonna be the one who is running the entire show. Going now to the other point under database, besides data, personnel, hardware, now it's the software. The software is typically the interface among users, hardware, and data. Any software is typically the entire goal behind it is to allow us to give instructions to hardware. We are going to also deal with operating systems. Most of the time we don't have a choice. It's mainly, in most of the highway agencies, it's window based, and it operates most of the computers.